নিয়ে সমগ্র রাজ্য দেশ এবং পৃথিবীর বিভিন্ন প্রান্ত এই উপলক্ষে একটা ইংরেজি খবর বিখ্যাত নায়িকাকে বলেছিল তারা কি ভাবছেন এই বিশেষ ঘটনাটা নিয়ে এবং আমাদের সমাজে নারীদের প্রতি যে দৃষ্টি যে আচরণ তা নিয়ে। প্রায় প্রত্যেকে বলেছেন সমাজের সভ্যতা নারীদের প্রতি এবং নারীদের শুধুমাত্র মুক্ত হিসেবে দেখার যে দৃষ্টিভঙ্গি আজকের দৃষ্টিকোণ রয়েছে তাতে পচা গলা সমাজকে কি করতে যাবে তা আপনারা জানেন। দর্শককে সাংঘাতিক শাস্তি দিলে কি সমাজটা প্রস্তুত হয়ে যাবে এই মনোবৃত্তিটা বদলে যাবে এটি তারা সন্দেহ প্রকাশ করেছে। একজন নায়িকা বলেছেন তার বালিকা বয়সের কথা কিশোরী বয়সের কথা এখানে বাজারে গেলে বাসে উঠলে ট্রেনে উঠলে শারীরিক নিগ্রহ একবারে বাঁধা ছিল। তিনি তার 16 বছর বয়সী এক
So, very good afternoon to everyone. Hope I am audible to you, and I welcome you all to today's live interactive session on geosynthetics and reinforced soil structures. So, today is the fourth week of discussion. So, 1/3 of the course we have actually already covered. So, 1/3 course we have covered, and we have 2 more months of the course that is upcoming, right? So in this 1 month, what we did was we just introduced the basic concept of geosynthetics and reinforced soil structures. We saw what the different types of geosynthetics are. Then we saw which geosynthetic is used for what purpose. After that, we also saw that how is the mechanism of reinforced soil, means what is the mechanism that actually takes place in case of reinforced soil structures that we saw. Then we also solved some basic problems from earth feature theories. Then we solved some problems from those basic concepts of soil reinforcement. Then we saw some tests regarding different types of geosynthetics, some strength tests, then tests to determine various hydraulic properties, right? All those things we saw. And in today's lecture also we won't be discussing, we won't be proceeding that much ahead, but just we will be discussing the basics of reinforced soil retaining wall. Okay, the basics, and what are the main basic steps that we have to follow, or what is the stability calculation, or the stability analysis that we have to do in order to design a reinforced earth structure, right? And in the next class will be on the 20th, that is on Tuesday. Tuesday from 6 p.m. to 8 p.m. The next class, what we will do, we will try to, that class will be actually quite important because we will try to solve some problems, right, regarding reinforced earth retaining walls. So that will be little bit. So 20 to the so the class of 25th August is is preponed to 20th, right? So coming Sunday, that is 25th of August, we won't be having an interactive session. Instead of that, that session is preponed to Tuesday from 6 p.m. to 8 p.m. Okay, generally we have 3 to 5 p.m., but as it is a working day, so we will be having from 6 p.m. to 8 p.m. Okay. Yeah. Now I don't know how the weather is at your place, but here at Kanpur since a few days it was very hot and humid. It was not raining; it was very hot. And but since a few 1 hour back it started raining, so weather has just cooled down a bit here now. Else it was like very hot since a few days. So let us start today's discussion. So if you remember in the previous class also we had actually discussed about the external stability. Okay, we discussed about the external stability briefly in the previous session. We had discussed the external stability calculations briefly, right? So if anyone can tell me what are the main external stability checks that we have to do, what are the main external stability checks that we have to do?
Sliding, overturning, bearing
Uh,
capacity.
coming actually, it's very low.
Sliding, overturning,
It's
bearing capacity.
very faint. Not coming.
Am I audible now?
I cannot hear. You can type also. There is no issue. I cannot hear you. It's not audible.
It's not. It's not.
Your hearing capacity, right? Hearing capacity. These are the main sliding overturning and hearing capacity. These are the main three, and also along with that, we have the slope stability, right? The stability of the complete step, right? Uh, my voice, can you hear?
Yeah, it's audible.
Okay. But your voice, I don't know why it's coming very faint.
Let me check.
Cannot hear. Very light voice it's coming. Very difficult to hear. Okay. So let us start then. So basics, external stability analysis. We have stability against lateral sliding, overturning, bearing capacity, and the overall failure. Overall failure is nothing but the complete this squeeze circle failure, right? The overall failure. Then to determine the length of the reinforced block. Okay, so to determine the length of reinforced block, so that is also a calculation that we will do. We will see that how we calculate the length and all, length of the reinforced section and all these things that we will discuss in detail in the, when we solve problems regarding the main design of reinforced blocks. Okay. Okay, so one more thing also we studied. I hope you remember the lateral earth pressures, right? The active earth pressure, the artifact pressure coefficient, and all those things. What is the how to calculate the Coulomb's earth pressure coefficient, the Rankine's earth pressure coefficient, all those things. I hope that you remember. Now, the next thing is embedment depth. Embedment depth is nothing but how much, like the reinforced wall you are constructing, something like this, right? So how much you should embed it below the soil. So there are various criteria given by various codes. So but the FHWA criteria for embedment depth is actually given here. So if uh, there is slope in front of wall, and the wall is actually horizontal wall, then we have to use h by 20 as the minimum embedment length. Then we have an abutment, we have horizontal abutment in front of the wall, then we have to use h by 10, and the abutment, that slope of the abutment is taken. So for various slopes of abutment we need to use various abutment.
Excuse me,
Various,
Ashish, could you make your voice a bit more louder,
yeah, sure.
please?
Please, Ashish.
Hello. Yeah. Now you can hear me, right?
And please keep your mic close to your
Oh,
mouth, because as you move about we don't get the voice. And you
okay.
really
Okay.
speak something knowledgeable. I'm missing it very badly.
Okay. 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 I will try to speak like that. Okay. So yeah. So as I was saying that this there are various codes that have given various specifications regarding the embedment depth. Right? So embedment depth is nothing but how much we should embed the retaining wall, like the retaining wall below the soil. Right. So for various slopes, various degrees of slopes, we have various embedment depths it is given, and the minimum embedment depth that is recommended is 500 millimeters.
Is it for
All right.
the leveling pad or the reinforced block?
So it is given a minimum embedment to the top of leveling pad. Means from here
Okay.
to the top of
Hmm.
leveling pad, it should be that much.
Yeah,
Where
yeah.
is it? Yeah, yeah. From here to the top. This is the leveling pad, say. Then to the top of the leveling pad, that much height. Yet anyways, if you when you consider reinforced block, it will be here like this only. It will be constructed like this only, right? So
Right,
this
right.
is will also go down only.
Hmm.
Because ultimately, the main purpose of giving this amendment is what? To give give a support, right? So you cannot have just the front. You cannot have just the front. This facing embedded like that, and wall you can construct. It is not possible, right? So whole thing will be obviously embedded here.
So what if I embed the panel but don't embed the reinforced block?
Then what will be here? So you are telling that you are you will here you will be having normal this soil, and here
Right, right, right.
no, that we don't do generally from because here we will be having one panel, right? So here also we'll attach one reinforcement like that. We will.
But that panel is supported in both ways.
Yeah, yeah, yeah. It will be supported. It will be supported from here also, and this embedment will also be giving some support. So as you said, so there are these main three types. First is the sliding, then overturning, then other is the bearing capacity, right? So for sliding, so we have a wall, we have the wall, right? So and we have the earth pressure acting like this. Okay, earth pressure. We have the earth pressure that is acting. Then we have some surcharge here. Okay, some surcharge here. Due to that surcharge, we will be having some. So this is P1, this is P2, and then other say some horizontal load we have like this PH, right? So this portion, this is coming from the right active earth pressure of the backfill soil. Then this is coming from the what? From this and this. The active earth pressure from the surcharge, from the permanent surcharge and the live load surcharge, right? And this pH is the horizontal force. It is coming sorry, not this, coming from the say your this crash barrier load or something like that. All right. So all these three loads, horizontal loads, you need to consider for the lateral sliding. So if you see all this p load, this complete p load will be acting in this direction, acting in this direction. So what it will, it is a disturbing force, right? It is a disturbing force. It acts in the acts in to destabilize the retaining wall, right? It acts to destabilize the retaining wall, right? It acts to destabilize it. So what is it is pushing the retaining wall, right? It's this force is pushing the retaining wall in this direction. Okay, so it is destabilizing. So what will be the resisting force in that case? What is the resisting force in that case? The resisting force is nothing but the friction that develops at the base. Okay, the friction that develops at the base. So the frictional force that will be developed at the base of the reinforced block and the foundation soil, at the interface of the foundation soil and the base of the reinforced block, the frictional force that will be generated, that will actually be what, preventing the sliding of the whole block, right? Say there is no friction, then what will happen? Due to lateral force, it will just keep on sliding, it won't be stable. But as there is some frictional resistance that is there at the interface between the reinforced soil block and the foundation soil, that frictional force or the shear resistance will actually be prohibiting the sliding of the reinforced field, right? So what is the shear resistance? Shear resistance is nothing but mu. This mu is the friction coefficient, the friction coefficient between the reinforced soil block and the foundation soil, right? It is a friction coefficient between the reinforced soil block and the foundation soil. So the friction coefficient times the what, times the vertical load. Vertical load at the is at this level, what is the vertical load? Gamma into h into l, right? Gamma is the unit weight of the soil, h is the height, and l is nothing but the length of the reinforced block, this length. Let me draw it properly. So this length of the reinforced block, reinforced field, okay, reinforced block, this length is l. So length plus the dead load or the permanent dead load that is there at the top side, the pavement weight, the weight of all the structures like the crash barrier load, all the things, the median weight, the weight of the median, all those if you sum it up, you will get this qd times nothing but the length. Like, and if you notice here, you will see that while we calculate the resisting force, while we calculate the resisting force, we have not considered ql, right? This ql we have not considered, so please keep that in mind, right? While we can calculate the destabilizing force, we consider both qd and ql, but when we calculate the resisting force, we only consider ql. Okay, that times we do not consider ql because we want a conservative result, right? Conservative result, that's why. And the factor of safety against sliding minimum, we should have a factor of safety of 1.5. Okay. And this is the case of back-to-back walls. When we have back-to-back walls, so what is suggested here that this the various codes have suggested various things. So this K generally changes when we have this overlap. So this overlap distance you can see here. So this is the what? This is the active wedge from this wall, and this is the active edge from the other wall. Okay, from this wall, this side, and this is the overlap length. Okay, overlap length. Now some conditions are given. If the overlap distance d is 0.3 h, then k equal to 0. That means the sliding check is not required, right? K is equal to 0 means this what, this, there is no this lateral earth pressure we are considering. Okay, that means sliding check is not required if the overlap distance is 0.3 h. Okay, okay, if the overlap distance is 0.3 h or more than that. If the two blocks are very far, two blocks are away, then we take k is equal to k, k is equal to k, and if the overlap distance is less than 0.3 times of h, then we do the interpolation between k and 0. Okay, 0. Okay, that's all. So these things we will see later if we need while doing some solving the problems. That time it will get clear. Okay. Yeah. Now next is the what, factor of safety against overturning. That is the overturning stability. So similar to whatever we saw in sliding, those are the forces will be same, right? The forces will be same. Those are the what, destabilizing forces. Those are the what, destabilizing forces. Those are the destabilizing forces. Now these forces are also what? Also are giving a moment like this, a disturbing moment like this. Okay, the disturbing moment about this point, a disturbing moment. This disturbing moment is what? Trying to trying to turn the turn the retaining wall in this direction. It is going trying to turn this retaining wall, right? Now this is the disturbing force. And what is the what are the resisting forces? Can you tell me what are the resisting forces that are acting? What are the resisting forces that are acting? These are the what you saw. These are the disturbing forces, right? So these are the what? These are the contributing to the disturbing force, right? The disturbing force, the lateral earth pressure and all those. These are the disturbing forces. Now, what are the resisting forces that are acting? Can you tell me? What are the resisting forces that are acting?
Weight of reinforced soil and
What?
dead load. Weight of reinforced soil
Weight of reinforced soil and
and dead load of the
right.
structures.
Right. Right. So weight of the reinforced soil, as the reinforced soil is weight of the reinforced soil and the dead load both are acting like that. So you can see the moment will be acting like this, right? Like this. So it is acting opposite to this. It is acting opposite to this. It is acting opposite to this. Alright, so that is our resisting moment. So that is what, so the overturning moment is calculated here. So this P, this P due to the earth pressure that is acting, that acts as a height of h by 3 from the bottom. So that h by 3 times this this term they have done, h by 3 times half kab gamma h square. So you get 1 by 6 kab gamma h cube plus half kab. So this, then we have this rectangular variation, right? So rectangular variation that is acting at a height of h by 2. This is h, then it is acting at h by 2 level, h by 2 level. So h by 2 times kab gamma qd plus ql into h. So half kab qd plus ql into h square. And next is our this ph that is acting, at what? It is acting at a height h from the bottom. So ph times h. So it is the overturning moment. Now what is the resisting moment? Resisting moment is nothing but from the weight of the soil, from the weight of the soil, right? So weight of the soil, so weight of the soil is acting like that here. So this is L and this is what? L by 2. So that L by 2 are getting here, gamma into h into L into L by 2 plus same qd into L by 2, same due to the dead weight, same thing, right? And also here also you can see in the calculation of resisting moment calculation, we have ignored the live load. Okay, the live load is not considered, only the dead load is considered. Okay, so now here's the minimum factor of safety that we should have, that is we should have minimum factor of safety of 2. Okay, so we will always try to keep uh, the factor of safety above 2. Okay, now the third thing is the bearing capacity check, right? The bearing capacity. So first, to calculate the bearing capacity, what we need to do, see, so you have, sorry, so you have the wall, we have the reinforced block here, L, reinforced block here. So see, there is the what is the pressure that is acting. So the weight of this reinforced soil block, this is giving some vertical pressure onto the foundation soil that is here. Here we have the foundation soil, right? So the weight of the reinforced block that we have to consider. Then we have to consider the live load and the dead load. Okay, so you can see here, so gamma into h into b is nothing but what? Nothing but the, see now L they have considered this as B. Okay, length of reinforced block, consider B. So I will write here B. So gamma into H into B plus QL plus QD times B plus any other permanent load. So any other, if there is any other extra load that is acting to the vertical load, that also you have to consider. Okay, so with this you will get the total vertical load. You will get the total vertical load. Then what you have to do, already you have calculated the resisting moment here. Already you have calculated the resisting moment. So resisting moment divided by RB will give you the eccentricity, right? Give you the eccentricity. Now what is the eccentricity? Now see this is the base B, right? So this is the B length. Now the vertical pressure, if you want to represent it as a point load, if you represent, so say this is B, right? Right, and say this is the center. This is B by 2. This is B by 2. Now what is the eccentricity? Say the total load that is coming, that if you want to represent as a vertical load, single vertical reaction will be that correct term. If you want to represent that as a single vertical load or single vertical reaction, so that vertical load will be acting at some eccentricity at the base. Okay, that vertical load will be acting at some eccentricity at the base. Okay, so that eccentricity you have to find out. Then after that we have to calculate the the bearing pressure that is acting on the foundation soil. Bearing pressure that is acting on the foundation soil. So how will we find that out? We will use the Meyerhoff's relation, RV by B minus 2IC. So B is nothing but this is B, the width of the reinforced block, and we deduct 2IC times, because it was seen by Meyerhoff that uh, the soil the reinforced block actually loses contact with the foundation soil 2IC on both the sides. Okay, so that 2IC we deduct. Okay, so that will give us the main bearing pressure that is acting. Now this bearing pressure should be always less than the bearing capacity of the soil, or the allowable bearing pressure of the soil. Okay, allowable bearing capacity of the soil. Also, one more thing, you ensure that the eccentricity is should always be less than B by 6, and eccentricity will always be less than B, should always be less than B by 4 in rocks. Now why, can you tell me why we have this criteria? Why do we have to ensure that the eccentricity should always be less than B by 6 or B by 4? Generally B by 6. Why do you have to ensure that the eccentricity should be less than B by 6? What is the reason? What is the reason for this?
Otherwise, the foundation will lose contact with the soil.
Why? Why does that
Because
happen?
of
Because of overturning moment, increase overturning.
Not, that is not. You are right that it will lose contact, but why will it lose contact?
because once it will be in inclined position, one side up and other side down.
Yeah, but why that is happening? Think in terms of pressure.
Because of eccentricity.
Yeah. So what happens is that because of its eccentricity, see generally the what? If I this is B, and if I plot the bearing pressure at the base, so it will be something like this. Okay, something like this. Okay, something like this is here it will have one value, here it will have one value. Okay, so like this it is right. But what happens if the eccentricity is more than B by 6? What happens is you will have tension that develops at one side. Okay, tension. So if
Okay,
this
okay,
is like
okay.
understood,
Yeah.
tension develops that are negative pressure. So due to that, there won't be any contact between the, and soil, is it's weak in tension. It cannot take tension. So due to this tensile
Right.
pressure, it will have the contact will be lost between the base and the foundation soil. Okay. You might remember this relation. So Q max is equal to what? I also forgot. Uh, B by B, like this something is there, right? 1 plus 2IC by B, this relation, right? And Q mean is nothing but V by B1 minus 2IC by V. Right, Q max and Q min. This is the Q max and
Yeah.
this is the Q min. So if this E is actually greater than your B by 6, then what will happen? Then we'll have negative, Q min is negative. Right? You will have Q min as negative. So you will have some negative tensile forces due to which the contact between the foundation and the soil will be lost. It is the reason. Just a second. Huh? Yeah. Now types of bearing capacity failure. This you should know. So what are the types of bearing capacity failure? What are the types of bearing capacity failure?
General shear failure, local shear failure, and punching shear failure.
General shear failure, general shear failure, local shear failure, and punching shear failure. So general shear failure generally occurs if the soil friction angle is generally more than 36 degrees. Else below that we consider general local shear failure, and if the soil is very loose, the shear faces will actually won't develop shear surfaces, then that time we have the punching shear failure. So this we won't go much into detail. So this is all these things are already discussed in basic soil mechanics courses, so that we won't be dealing with in detail. Now I said one thing, right? So this pressure that is coming, there should be less than the what, the allowable bearing pressure of the soil. The allowable, it should be less than the allowable bearing pressure of the soil. Now what is allowable bearing pressure? If you can define what is allowable bearing pressure or allowable bearing capacity? Allowable bearing pressure only, sir. What is the allowable bearing pressure or allowable bearing capacity, whatever you want to say?
Maximum pressure with which the settlement is within permissible limit.
Correct. So one is the settlement criteria, correct? Another is the bearing capacity criteria, right? So there are two, bearing capacity criteria and settlement criteria. So the minimum of the two we consider as the allowable bearing. Okay. Now, bearing for the estimation of bearing capacity, all of you might be knowing this code, very important, IS 6403. This is the code that we use for the calculation of bearing capacity, and to check the settlement we have the immediate settlement calculation, the consolidated settlement. So this immediate settlement calculation, consolidation settlement, these all those things we have already discussed in our basic soil mechanics course. So immediate settlements is one element, nothing but the immediate settlements, that elastic settlement that occurs immediately after loading, right? So QP E by 1 minus mu square, like that some relation is there which actually gives us the what, the immediate settlement, right? I forgot the relation if it is there. Yeah, QB 1 minus mu square by E. Right, so that is the what? Immediate settlement. QB E 1 minus mu square. And then we have the consolidation settlement. This consolidation settlement also you have studied in your what to say, basic soil mechanics course. Okay, this is the coefficient of compression, all those things. So there, this give the primary, and for the secondary consolidation we have one more factor, that is alpha, that also you have to consider. Okay, so all these things we calculate the settlement of the soil, we can calculate the settlement of the soil, and we can check what is the pressure corresponding to the settlement that will become. Okay, so we won't get much into it. We will solve some basic problems towards the end of today's class from this bearing capacity. Okay, let us not go detailing this. And the fourth one is the overall failure check, right? The slip circle failure check. So what we do, so we consider, so this is a trial and error method, right? So this is a trial and error method. So generally various softwares are there that will be that will help you to perform this analysis, because doing this by hand, it's very tiresome, right? It's very tiresome and it's very lengthy. So nowadays there are very a number of softwares or computer codes are actually available commercially or in open source also, that actually helps us to do this analysis. So we first, what you do first, you select a slip circle. Okay, you select a slip circle, then you divide the slip circle into several wedges. Now for one wedge you can see, so this is one wedge like this. This is one wedge. Let me draw it a little bit nicely. So this is one wedge. Okay, in that one wedge, see the weight is acting downwards like this. Now this weight can be divided into two components, right? So one is this normal component and other one is what? This shear component. Now this shear component of the weight, this component is actually what? Destabilizing the soil wedge. Destabilizing the soil wedge, right? So if this angle is alpha, so and this weight is I, it is Wi. So what is this? What is this? What is this? Can you tell me? If this is Wi, this angle is alpha, then what is this? Wi sine alpha, right? Then what is this?
WI tan alpha.
This is
Cos
Wi
alpha.
cos
Cos
alpha.
alpha.
Wi cos alpha. Now, see, this is our destabilizing force, right? So for all the wedges, what you need to do, for all the wedges you need to calculate these wi's, all the alphas you have to calculate, and then you have to sum it up. So what is our factor of safety? Factor of safety is nothing but summation of resisting forces by summation of what? Disturbing forces. Now say the soil has some cohesion C, then the fast restoring force that will be coming is cohesion times the total length of this arc, this will give the first term, C plus C into LA. Okay, C into LA, cohesion times the total length, plus next we have to write the frictional resistance that will be occurring. Frictional resistance. Now see, frictional resistance always is what? What is frictional resistance? So say you have a block, of wood, of weight W, okay, of weight W lying on a plane surface. Now what is the frictional force that is acting here at this surface? If you want to write, or say not plane surface, let me draw it like this. So what is the frictional force? The normal force times the the friction angle. Normal force times the friction angle. Now what is the normal? So normal force that is acting is Wi cos alpha I. Now a reaction force will be acting opposite to that, of the same value, Wi cos alpha I. A reaction force will be acting, right? A reaction force will be acting at the same, of the same value. Okay, so that much it's acting, right? So the reaction will also be there, normal reaction force. So we have Wi cos alpha I times what? Normal force times what? Friction angle. Friction angle is what? Nothing but tan phi, we consider. Tan phi. Friction coefficient. Tan phi will give us the friction coefficient. So that's all. And we do summation of this because all the wedges, right? So we sum it up. Plus, now in your case, what you will be doing is that you will be using some reinforcement. You will you will be using some reinforcement, right? You will be using some reinforcement. That reinforcement will be having some allowable tensile strength, say T, that will be mobilized, TR. So that TR times the what? Times this lever arm, that is H. So this will form our resisting force. Divided by what is our destabilizing force? The sine components of the weight. All the summation of the sine components of the weight. Okay, that will be the destabilizing force. So like this we have to calculate. Okay, so this we do, first you do for one arc, then you change, then you draw one more arc like this, then you calculate again. So like this you need to keep on taking thousands of arcs and you need to calculate like this. And all the arcs, for each arc you will get one factor of safety. So the least factor of safety, the arc which gives the least factor of safety, that is your slip circle. The final slip circle, that is the factor of safety that of the whole structure. Okay, so like that you need to calculate. All right. So if you get time, you will solve some problems from this also. It is very easy
What is
problems.
small h?
So small h the lever arm, na, from this is the point of rotation you are considering, and this
Right.
TR is the reinforcement. Say you have a reinforcement here like this. So the height of the the distance of the reinforcement from this point of rotation, because you are taking moment about that point, right?
Okay, okay. That means it will be HI. H will be different for different wages.
Yeah, for different. So here you will have say one more T. So this will be like another H like that. H
That
will
means
be
summation of TR IHI.
like that. So here only we have considered one T, one
Right,
reinforcement.
right. One reinforcement. But in the formula,
Yeah.
it will be HI, na?
Yeah. So here we have written H because just one we have considered, right? So here just one T you have considered. That's why you have written only that H only. That's the reason. Else
But
you are
for
right.
other
Yeah, we will have HI. But other component for all
okay.
we are considering, right? So in this case you are considering that only one reinforcement, say like this, it's there here. That's so now say one more reinforcement would be here. Then one more we would have considered. Like that.
For each wedge, each vertical wedge, there will be several horizontal reinforcement.
Reinforcement, see, just forget about the wedge. So this up to this part. So no, sorry, not this part also. See. So this part is separate, right? Only this length times LA, this LA times CA, done. Then this part
Yes.
is for wedges. This will be for all the wedges, right? And this is for the reinforcement part. Now say your wedges are only 1, 2, 3, 4, 5, 6. Now, but you may have 10, 20 T's here. So all these T's you have to consider. Okay. So at that
For
time it
each
will.
wedge also, I have to consider several reinforcements at different level.
Yeah. So wedge, see, for wedge, this is the thing. This part is the thing. This is the thing for wedge. This part. Okay. This,
Okay.
this part is for, so this is for the reinforcement part. This
Total
is what is the reinforcement. Treat this as a separate entity. Don't connect with the wedge.
Okay.
Don't connect with the wedge. So I understand that you might be thinking that for this wedge, this T like that. Not like, don't connect with that wedge. Okay. So keep this separate.
Okay.
So, but this part is separate. This is for the all the wedges and this part is separate. Okay.
Okay.
This part is separate. So this you have to see how many reinforcements are passing through your slip circle. So whatever number of reinforcement, that summation, that you have to sum HI. Okay. Summation TI HI. Okay. Now we have the seismic load. So seismic loads also, these basic how to consider seismic loads you already know from you already all of us have done the our building designs, right? In our BTech courses we have done this design of buildings, reinforced concrete, right? So there we have considered these seismic loads, and for that we use this our one and only IS 1893, the latest of which is 2016. That code we actually used. So from that code, we have to calculate the base acceleration factor alpha. So so for a certain zone, for a certain importance factor, right, what we do, we calculate this alpha. Okay, alpha. And this A by G is nothing but what? SA by G is what? SA by G is what? Spectral acceleration coefficient that we calculate from this plot. Okay, this spectrum, acceleration spectrum that is given to us, and this spectra that is given in the code, and from that code we can take this SA by G. Okay, so calculate this SA by G. And I is nothing but the importance factor. So importance factor is also given here. So what are the typical importance factors that we calculate? So that we have to consider, that is given here. So what do you do? We calculate the alpha value. Now alpha value, after we calculate, we convert it to alpha m using the FHWA formulation. Okay, so alpha m is nothing but 1.45 minus alpha times alpha, and this alpha m we use it in our design of reinforced earth walls. Okay, this alpha m we use in the design, so we will see that in the upcoming slide. So in the next class, we will be solving some problems for, hopefully we will be solving some problems for design of reinforced earth walls. In that case, probably I'm not sure what is there in the next class. Probably we will be solving, I'm not sure. But if we solve, we will see that we won't be consider the, while I solve, well we solve here in this interactive session, I won't consider these seismic loads. But what you do after, so I will be solving the problems, right? I will be solving some problems where I won't be consider the seismic. But what you again, you solve the problems by yourself by considering the seismic loads. You will see that sir will solve some problems. Sir has solved some problems in the class here, where he has shown some examples how to calculate using the seismic loads. Okay, so following that, you try to incorporate the seismic loads and try to solve those problems again by yourself. Okay, we will see that later. And this map you are well aware of. This is nothing but the seismic zonation map. So the whole northeast region is comes in this our zone 5, that is the highest level of seismic severity zone. That is the zone 5 zone. The whole northeast. Then we have the Gujarat, some region is there in zone 5, and in Uttarakhand, Himachal Pradesh, and JNK near Nepal border, we have some patches of zone 5. So this northeast region is maximum, it is like high seismic activity region because of the our these plates, right? The Eurasian and the this Himalayan, these plates are there, which actually are constantly moving towards each other, due to which there is constant seismic activity in this region. And especially in the this eastern India, when we construct in the northeastern India, we have to, like, all over we consider this seismic forces, whether it is in Delhi or northeast or South India, everywhere we consider, but especially when we consider high seismic zones, that time we have to give some special attention. Okay, so this is the seismic zonation map. Now, if the seismic load calculation, so seismic load calculation, so there are two components. The two components. One component, so see, you have the retaining wall, right? So you have the retaining wall. Here you have a certain, so this much portion is a reinforced portion, and then you have the backfill portion. So this is the reinforced portion block, and this is the backfill block. Now, so when earthquake, there will be earthquake, there will be some ground motion there, ground motion that is occurring. The inertial force of both the reinforced block and the backfill block will be acting. So what? So we consider those two inertial forces as a separate entity, right? So one inertial force will be what? This backfill. This backfill will be imposing some inertial force on the reinforced block. This backfill is going to impose some inertial force on the reinforced block. So that inertial force is given by nothing but this PAE. PA is equal to 0.375 times alpha m that you saw in the previous slide, alpha m times gamma into h square. H is nothing but the height, and this PAE acts at a height of 0.6 h from the base, 0.6 h from the base. Now this is the inertial force whatever the backfill block is imposing on the reinforced block. Now next inertial force is the the inertial force that is uh, uh, acting because of this this reinforced block itself will be having some inertial force, right? That will get, so that is nothing but 0.5 alpha m gamma into h square. So these two we sum it up, and while summation you see that PIR is considered wholly, but half of PAE is only considered. Okay, assuming that both the forces do not reach the peak value at the same time, just that we do not over design the thing, so that we do not over design our structure, we consider this. Okay, PIR plus 0.5 times into PAE. Okay, so that we do not over design, we consider this. Okay, so this is added to the, so you remember, now go back to your previous this one, overturning calculation, sliding stability calculation, all those things. There you considered some horizontal loads, right? For which you considered the sliding force and the moment, overturning moment. There you have to incorporate all these things. Okay, there you have to incorporate these loads also. Okay, there you have to incorporate these seismic loads also. All right.
Here the gamma of reinforced block and gamma of backfill
Yeah.
block
Consider
may be
same.
different.
Yeah, maybe different, maybe different.
Maybe
Yeah,
different. Okay.
that you have to consider accordingly. That may be different. So this is one more case, generalized case given by very famous Mononobe Okabe method. This is like the one of the most legendary works in the field of seismic the seismic earth pressure theories, that was given by Mononobe and Okabe. Okay, so two different papers there are there, Mononobe and Okabe, and together also they have given. So the MO method, Mononobe Okabe method. This is very famous. So in Manobe Okabe, they actually gave a generalized relation. Okay, generalized relation they gave it. So this is a simple only. You can see the total PAE that is acting, that is nothing but half into gamma H square 1 minus KV times KE. So KV is the coefficient in vertical direction. So see, generally earthquake has some horizontal component also and some vertical component also. Okay, some horizontal component also and some vertical component also. So what Mononobe and Okabe considered, so this is known as the pseudostatic approach. This is very famous. Pseudostatic approach. So the various other things were also developed later, like pseudodynamic approach. Okay, pseudodynamic approach, all those things. But this is the main primitive thing that is used everywhere till now, till date. Okay. So pseudostatic approach. In pseudostatic approach, the basic I will tell you. Pseudostatic approach, what is considered? Say you have a retaining wall, any retaining wall, cantilever retaining wall, whatever retaining wall. A normal cantilever retaining wall. Let me just. Okay. So there you have the active soil wedge that is acting. So in the pseudostatic approach, it is assumed that this wedge this active soil wedge, will be acting as a rigid body. It will acting as a rigid body, and the inertial effect of this rigid mass. This rigid mass we have to consider. So, so we consider that the earthquake forces is divided into two types. So one we have the K horizontal coefficient, and the other we have the vertical coefficient. Okay, vertical earthquake coefficient. So these are the earthquake acceleration coefficient, K, V on K. So K is nothing but A by G. A is nothing but A, you can consider the maximum acceleration that might come to that place, A by G. So this times the gamma times K, KH, this gives a horizontal vertical 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 load that is coming, okay, inertial load that is coming, and same gamma times kv will give the destabilizing vertical. So this is the so just you don't have to consider all these things, just for the your knowledge I'm saying all this. At least you should know the term pseudostatic approach, how all these things are developed, okay. So in that case, so here you can see it, that is on this. So how is PAE calculated? Half into gamma h square KAE times 1 minus KB. Now KB is the coefficient in vertical direction. So that generally we can consider 0. So if you are considering that only horizontal, the earthquake will only having a horizontal component and it won't be having a vertical component. What we consider is that we consider that what the kv is 0. So kv we generally consider 0, or because it is very much lesser than horizontal component, right? The horizontal component of the earthquake is very high than the vertical component. So generally we tend to ignore this case, okay. And kh is nothing but this alpha m. So alpha m is nothing but this k. So alpha m, you already saw the calculation, how to calculate. And ke, what is kae? What is KAE? KE is nothing but the active earth pressure coefficient. Generalized relation for the active earth pressure coefficient. So then we get PA is equal to half gamma H square 1 minus KP into K. Okay. And out of that, if PA is our static force that acts at height, P means PA is nothing but half gamma H square KAE. This is the static force. And PAE is what? PAE is nothing but the that from the your earthquake. Okay, that is the PAE. So PAE minus PA, that will give the dynamic component, the extra dynamic component that is actually acting. So PAE includes both earthquake plus static, and PA is only static. So if you subtract these two, you will get only the dynamic part, that is this delta. Okay. Just a second. Just a second. Just a second. No? Shared one link with you. And then searching.
Ashish, we have lost you.
Yeah, just a second. I will share a link. I am just seeing the link. Searching for a link, I will share. So there, that seismic analysis of retaining wall is given. That will be actually helpful to you. Yeah. Just share with you. Yeah, so see, you can see this video, okay, later, not now. I will share the link. Yeah, I have shared the link with you. You can see this video here. The seismic design of retaining wall using this Onobe Okabe method. Everything is clearly given, discussed. Okay, this is by Professor Kaushik Dev, that you can see later. Okay. Now, total forces are the sum of the seismic forces and other static forces due to self-heat plus surcharge. This that we actually know. Allowable factor of safety when seismic forces are included 75% of the corresponding system. So see, before, when it did not consider the seismic forces in an analysis, just the static forces we considered. That time we said that the factor of safety against lateral sliding should at least be 1.5, right? But when you do the sliding check, considering the seismic forces, at that time what we do, we consider 75% of this 1.2, this is 1.125. So you reduce the factor of safety criteria a bit, so that we do not over design again, so that we do not over design too much. We reduce the factor of safety a little bit, so that we can relax the criteria a little bit. Okay, because we are adding seismic forces also. Okay, so that we are using seismic forces also, just to relax the criteria a little bit. We reduce the factor of safety by 75. Okay, 75 for 1.9, 1.125 we consider. But similarly, for overturning, the factor of safety should be 2. So 0.75 times of 2, that much you have, that much of the minimum factor of safety you have to consider in case of overturning. Okay, that is what is discussed here. Okay, now yeah, internal stability. So what are the internal stability? We already discussed this, right? So what are the various internal stability criteria that we have to consider while the designer retaining wall? What are those? What are the various internal stability criteria that we have to
Uh, Before
consider while
proceeding
the,
further, can you
yeah, yeah,
just explain the internal stability and external stability concept? What is the difference
yeah.
on this approach?
So external stability we discussed just now, right? So overall stability, you the overall stability. So you have put the reinforcement, everything you have designed, right? Now,
Right.
whatever you have designed, overall the structure, whatever you have designed, the stability of overall that thing, that is nothing but the external stability. Overall, whether it will slide or not. Now see, you saw that you have given, say, uh, n number of reinforcement, right? Everything you have done, you have constructed the retaining wall, you have checked everything, you saw that our wall is very strong, it is able to take the load from the top, everything, right? Fine, you are satisfied. Now what happens now, if the foundation soil is only not able to take the load of this wall, then what is the use of designing this reinforced earth wall? There is no use, right?
Hmm. Right.
So that is the external stability check. The whole structure as a whole, after designing, that should be overall structure should be safe externally. Externally are this, should be safe in sliding, that we discussed, bearing capacity and overturn. So the overall structure. Now, internal stability refers to the stability of this, whether the reinforcement that you are putting, that is able to take the load or not, whether it is going to rupture or whether it is going to not rupture, whether it's going to get pulled out of the soil or not. Those things, those checks are the internal stability checks.
Okay.
Okay, okay, it will be clear
Yeah.
when we
Yeah.
solve right? When we solve the problems, we will do all these calculations. Internal stability calculations, we will find out the vector of safety. From internal stability analysis, we will calculate the length of the reinforcement. All these things, when we do, it will be clear. Okay. So, so this is very simple, very simple, very simple. So, yeah. So I was asking internal stability. So what are the internal stability criteria that we should have? You already know this. What are the things? One is rupture. What? Your reinforcement should not break apart, tear apart, rupture. What is the second one? What is the second one?
Pull out.
First one, pull out. So what is pull out? What do you mean by pull out? When does pull out happen?
Inception
In the,
reinforcement.
friction,
Yeah,
Tensile
anyone
strength is
can.
less.
interface
What?
frictional force is less than your tensile
Internal friction
force.
less than whatever load that is coming, right? Whatever shear
Yeah.
load that is coming. Yeah, that time we have pull out. And when do you have rupture?
Rupture is when the reinforcement itself breaks.
Yeah, when the strength of the reinforcement is less than whatever that is
Less.
coming.
Yeah. Yeah.
And the third one that we not discuss earlier, but that is nothing but the connection failure. So you are connecting the reinforcement to your this wall, your facing block, right? We're connecting the reinforcement to the facing block. In the last class, we saw some videos also how
Yeah.
that are
Yeah.
connected. Right? So if that connection only breaks apart, then what is the use of, like, how you might have used titanium reinforcement, but what if the connection only breaks? That time no use of anything, right? So that also you have to ensure that the connection is also strong enough that it is able to hold, the reinforcement. Okay. And if the connection is weak, what will happen? The facing will also move apart. There will be excessive deformation. All these things will also be there. So these are the three main: rupture, pull out, and connections. Okay. Now one more important what to say? One more important point here is the long-term allowable design strength. Long-term allowable design strength. So what we do various tests, and we calculate the ultimate tensile strength of the reinforcement, right? We calculate the ultimate tensile strength of the reinforcement. Now that ultimate tensile strength of the reinforcement, that is a lab. In the lab, you are testing the reinforcement in a very controlled environment, right? In a very controlled environment, you are testing the reinforcement. You are doing your test. You are doing the experiment to find out the ultimate tensile strength, ultimate load of the reinforcement. But in the field, when you put, there are various n number of factors that come into action. So out of those factors, some of the most important factors are environmental degradation factor, construction induced damage, and the overall factor of safety, and the creep. Okay, so these are the most important factors that come into play. So what is the creep reduction factor? So creep is what? So load is there, constant load. So as time passes, this say 10 years past, 20 years passes, what happens? There is some loss of strength in the reinforcement. So that is nothing that is defined by the creep reduction factor. Then you have the environmental degradation factor. So you have placed the reinforcement in the soil. So there is rain, there is sunshine, there is so many environmental things. There might be some chemical action of the from the soil, so due to some minerals present in the soil, all those things. So various factors might be there. So that might induce some damage in the reinforcement. So that also you have to consider. That is the environmental degradation factor. Then you have the construction induced damage. So while placing the reinforcement, say the laborers or whoever, whatever who are constructing, they do some mistakes. They do not handle the reinforcement properly. Right. So there is some tear at some places, or there is some problems are there. That thing also you need to keep in mind. So that also might happen. Another is the overall factor of safety. Right, so these things you have to consider. So corner actually, as I say, I have told you about corner. So corner actually defines that allowable design strength is the ultimate design strength by divided by the reduction factor. The reduction factor for chemical biological damage times reduction factor for creep times reduction factor for your construction damage. So this was given by corner. Okay. So various things we can consider. Some other all more factors are given here. You can see some of the important preparation factors. So now creep test. So this creep test, how it is done, we will see that. Okay, we will see that how this creep test is done. Yeah. So before that, let us just see this one also. So now we are seeing the before we go to the internal stability calculation, we are just seeing now we are just seeing what are the loads. Okay, what are the loads that are actually that are acting on a reinforcement layer. Okay, we have to put a reinforcement at various layers. So what are the various loads that are actually coming at at a reinforcement layer? So that different types of loads, those loads we are discussing now. The forces in each reinforcement. So we will be having the self weight of the soil, right? That is always there. Then we will have the uniform surcharge. Uniform surcharge is what? Dead load as well the live load. Then the breach abutment load. Say you are constructing the reinforced earth wall, you have to construct at the end of a bridge. So the weight of the breach abutment load that you have to consider. Then the horizontal load to the backfill due to surface tension. All these things we discussed very rightly in the previous classes that you have to consider. The crash barrier load, etc. Those you have to consider. And also these are the static loads, and apart from that the inertial force due to the earthquake, that also you have to consider. So all those loads that we considered previously, that all those loads also will be acting now also on each reinforcement layer. Okay, all those loads will also be acting now at now the breach abutment load, how to consider that, it is shown here. I won't be discussing it again, it's all given here probably, so I just won't be discussing it. So let us go to the next. We have this what to say you have a foundation like that, right? Say you have a foundation like this here. You have a foundation at the top of the reinforced soil block. In that case, what will happen? How the load is going to get transferred from the foundation to the your reinforcement. Okay, that you have to consider. So that how to consider the load, that is given here. Okay, so this is the block, so this is the distance t, all these things are given. We consider a active wedge here. All right, so now this h is given like this, and tz is nothing but the force or the load that is coming at each height. Okay, that is nothing but a th. Okay, now this fh is acting here at this block, so this is a crash barrier. Say this fh is acting like that, so from that load how will you distribute to the reinforcement, that is given here, given by this. So just slightly loosely we are discussing what are the loads that may be there. Okay, what are the loads that may be there? One is the bridge abutment load we saw. Then this bridge abutment load, only this force, how we are going to transfer, that we saw here. Okay, so next yeah, so now let us now see this force transfer to reinforced layer is nothing but kf. What is kf? Kf is nothing but the earth pressure, okay, of the reinforced block, the earth pressure coefficient, times the vertical pressure that is coming, times svz. svz, now what is svz? Svz is nothing but the spacing of the reinforcement at a depth of z. So you have a wall, so you have reinforcement like this, right? So now at a depth z, so we will see that you can vary the spacing also, you can keep the spacing. We'll see all these things, it will be crystal clear to you when you solve the problems in the next class. Okay, now today's class we are just discussing overall whatever it is. Next class we will solve problems, that time it will be clear to you what is spacing, everything, all those things. SV is nothing but the spacing between two reinforcement at a depth of z. So z is the depth at any z is any arbitrary depth. Okay, so what we consider, say this is the reinforcement, right? So we consider that this pressure is acting like this, SV by 2 here, SV by 2, it is distributed like this, SV by 2 up, SV by 2 down. Well, this is the reinforcement, and this pressure is getting distributed in this region, in this side, SV by 2 above the reinforcement, SV by 2 below the reinforcement. Okay, so that's why you are multiplying by SV. So this will give the load transfer to each reinforcement. So the vertical load, earth pressure times earth pressure coefficient times SV. Now, what is the lateral earth pressure coefficient that you have to consider? So at the top, the movement of the retaining wall is very less. So we say that that there the conditions are almost earth pressure at rest. So at the top, generally this K naught is considered. So as we go down, it reduces to Ka. Okay, so there are various criteria that are given by various codes that is lightly loosely discussed here. Okay, just see that once. Okay, you should be knowing just that there are some criteria. What is the actual mechanism? Why this thing is happening? Why K naught is considered? Right? Why K naught is considered at the top? Why you are not considering Ka over the whole height? Why are we considering K naught at the top? Why not Ka?
Because deflection is more. Deflection is more at the top.
Deflection is
More.
no, actually deflection is less. That's why cannot na. Earth pressure and rest.
Deflection is less. Sorry. Deflection is less.
Deflection is less. That's why we are considering cannot. That's the reason. So if there is deformation, so you remember this diagram, right? This is the earth pressure A. This is K naught, and this is earth pressure K coefficient Kp. So Ka is least. Why Ka is least? Because as the wall moves away from the away from the backfield little bit, there is a release of pressure. As the wall tilts a little bit away from the backfield, there is some release of pressure. That's why the K is less. Right, K is less than K naught. But what we consider is that there is no almost negligible deformation at the top of the wall. So the release of pressure is not able to occur. That's why the pressure is high at the top. We consider that K naught. That's why the earth pressure coefficient is high at the top. Why we consider that K naught is there. Okay, so that is the reason. Deformation is less at the top. Fine. So we saw the loads that are transferred. Now we come to the internal stability criteria. First is check for rupture. Rupture means what? The load coming into the soil should be less than the allowable tensile strength of the reinforcement. The load coming into the soil should be less than the what? Should be less than the allowable tensile strength of the reinforcement, isn't it? So force in inlet reinforcement for any depth should be less than the allowable tensile. So that we have to ensure. Then how do we ensure that? Now force in reinforcement at any depth Z is nothing but this we discussed SV times Kf times gamma Vp. Gamma Vp is nothing but the vertical pressure that is acting. Kf is given, SV is this. Now how to find out SV? You select SV such that Ta by Kf into sigma. Like this you calculate SV first. You fix the spacing. Right? Then you can find out the eccentricity at depth Z. Similarly, then from here you can find out sigma Vb. So how to calculate sigma Vb? That is actually given here. So sigma Vb you put here, Kf you know, Ta you know, you can find out SV. Right? How to? So see, the rupture criteria fixes the spacing of the reinforcement. Okay, the rupture criteria fixes the spacing of the reinforcement. So how do we define the spacing? Calculate the spacing. Spacing is calculated by allowable tensile strength Kf sigma Vb. Kf is this, sigma Vb is this. Ta you already know, you got from your laboratory test. You will know the Ta of your reinforcement. From that you fix the SV. So rupture criteria fixes the what? Rupture criteria fixes the spacing of the reinforcement. Okay, so this is very important. So rupture criterion fixes the spacing So this spacing, when you select, you ensure that there will be no rupture failure. Okay, so rupture criteria fixes the spacing. Now next is the pull out criteria, right? Now what does your intuition say? What will the pull-out criteria fix? So rupture criteria fixes the spacing. You saw here the spacing of the reinforcement is decided by the rupture criteria. Now what does the pull-out criteria fix? What do you think?
Length of the reinforcement.
Exactly, correct. Very good. The length of the reinforcement is fixed by the pull-out criteria. Okay. So appropriate embedment depth should be provided to prevent the pull-out criteria. Now see, you have the wall, you know the active soil wedge, right? What is this angle? What is this angle?
45 degree plus 5/2.
Yes, 45 degree plus 5 by 2. You know the height that you want to construct, h, you know, right? You know, right? Now at any depth z, this length, which is within the wedge, that you can find out
Right.
just from geometry, isn't it?
Hmm.
Just from the geometry you can find out.
Yeah.
Then you know the angle, you know the height. That's this length you can find out the within the wedge. The length you can find out from geometry. Now the question is how much embedment length should be provided? It is beyond the active failure wedge. That this embed length is what? This embedment length is actually holding the reinforcement, right? Else if you provide reinforcement only up to this place, the whole thing will come out. Reinforcement will come out with the active failure wedge, right? The wall will fail.
Right.
So
Right.
you need to anchor the reinforcement back here. You have to embed the reinforcement. So this embedment length is also very important. So this embedment length is calculated from the pull-out criteria. This embedment length is calculated from the pull-out. So this length, this L1, you will get from what? The geometry. And this LE, you will get from the pull-out criteria. Pull-out. So total length of the reinforcement will be L1 plus LE. L1 plus LE. So we will solve problems and you have to do this. We'll make one table, so we'll solve the problems.
For each layer, we have to calculate the L1 and LE.
Correct. Exactly.
Okay.
Then how to select, how to design, we'll see that when you in the next class. How will, so for each layer we generally will calculate, but we do not give different length to each layer, right? So it is in practice it is very difficult. It will be very tedious in the field. So generally we don't do that. Generally at the top portion we will put less length, one less length. We'll see that. We'll solve some problems. It will be clear to you. We'll solve some problems. In the next class, that time we will see. Very easy. These problems are actually very, very easy. It looks a little bit lengthy, but very, very easy and very interesting also. We'll see them. So you understood how to find out the total length. Now FHW recommends that this minimum is 1 meter. Okay, so minimum we have to give 1 meter. Okay, this is given by FHW. Okay, so minimum that we will give 1 meter. Now, as I said, how to calculate this LE? So LE will calculate. So now if LE is less than 1 meter, we will put 1 meter. If it is more than 1 meter, we will put that value. The value which is more than. So minimum 1 meter you have to put. So how to, so see, so this is the reinforcement. So there are frictional forces, shear forces that are mobilized at the top surface of the reinforcement as well as the bottom surface of the reinforcement. At the top, at the bottom, at the both faces, the frictional forces are mobilized. So we have two here. Now, what is the frictional force? How do we calculate the frictional force? Vertical load times the friction coefficient, isn't it? This is how we calculate the frictional force. Vertical load times the friction. Yeah, right? Vertical load times friction. What is load? Sigma V times LE. That will be the vertical load. Sigma B times LE. And what is the friction coefficient? Friction coefficient is nothing but alpha times 10R. 10 alpha. So 10 alpha is the what? 10 alpha is the friction coefficient of the reinforced soil. Times we reduce that by alpha, pull out interaction parameter alpha, we get alpha times. So you will see how these are calculated in the next. So pull out vector safety again, pull out should be greater than pull out resistance divided by the force inter reinforcement. Okay. So all these things. So LE see LE. So L is the total length. LE is, so this is what? This is L1 that I said in the previous class. This L previous slide. This L1. This L1 is nothing but this H minus Z by 1045. This part is nothing but L1. Okay. So we'll see that when you solve the problem, it will be clear how to. So the pull-out criteria is satisfied by the length of the reinforcement. The rupture criteria is satisfied by the spacing of the reinforcement. Okay. Okay. So when we solve the problems, we will see. It's very easy. Nothing to worry. These problems are very easy. A little bit lengthy, but very easy. This is the time 4:30. So half an hour. Okay. So testing requirements. So what are the various parameters that we should know? We should know the soil properties. We have to know the soil properties. We have to know the reinforcement properties. We have to know the soil reinforcement interaction factors. So soil reinforcement. So what do you mean by soil properties? What do you mean by soil properties? What properties do we have to know?
Shear strength properties basically.
Shear strength parameters, the CA5, CN5, right? Especially the C5 value. Then reinforcement property, what do we have to know?
Tensile strength.
Correct. Tensile strength of the reinforcement. Then soil interaction parameter factor, what do we have to know?
There's alpha factor.
Yeah, alpha. There is the friction that what alpha that will be defining the friction coefficient. Alpha times 10 pi will be giving the friction coefficient between the soil and the reinforcement. And last one is the reinforcement facing connection. Facing connection. Okay, so how strong is the facing? That also you have to test. Whether the facing and the connection with the facing the reinforcement is strong enough or not. Okay, so the friction soil properties, as I said, friction angle is determined from shear box test. Peak friction angle is generally used. Why peak friction angle is used? We
Peak
discussed.
friction strain is less
Yeah, correct. Strain is less because
than residual friction.
right? The peak friction. Now long term, so this shear box test, these are various types small shear box. So this shear box test you have to do direct shear test at the soil properties. Then we have the long term allowable design strength. Long term allowable design strength. Long term allowable design strength, as we discussed already. Okay, scrape by ultimate tensile strength divided by this chemical biological construction damage, all these factors. Okay, so these are given here. You can see installation damage, creep, chemical degradation, biological damage, joint or seam. All these factors you need to consider. Okay, means this by this much factor we have to lessen the ultimate tensile strength. Okay, that's all. Then to find out the ultimate tensile strength, what are the tests that are available? Wide width test that we saw in the previous class, in the second discussion session. I think we saw the video, wide width test. So that we have to do. That will give us the tensile strength. Okay. This factor of safety is generally 1.25 to 1. That is generally considered. Okay. And some default values are given here. Basic values are given. Now let us see this video. Okay. tests are very time taking tests. It's a creep, you can understand. So at one load, you have to do the test for many days, many months. But generally that much time we do not have, right? That much time we do not have. So this is a apparatus that is used to accelerate the creep test. So what we do the test at various temperatures. So we keep on increasing the temperature of the chamber and we apply the load and we note down the results. Okay, at various temperatures we keep for some time, we see the results, then we increase the temperature, we see the results. Like this we keep on doing the test. Then later what we do, we extrapolate those results to whatever creep values that we need. Say how much time that we need to extrapolate the result. Okay, we extrapolate that result. So this is the
How
accelerated
temperature is related? How
temperature.
temperature is related to creep? Accelerated creep?
Yeah, but to accelerate the test, what? So this is one hack. Okay, that is device. Generally, what we need to do, for creep test, we need to keep the sample at a fixed this
Okay,
one,
that
right?
is fine. That is fine. But how temperature will help?
What they are doing is that with change in with if the temperature is high, that this is nothing but polymer, right? So there will be some
Okay.
uh, weakening of the reinforcement, elongation. There means temperature will aid in some elongation, right?
Aid the elongation. Okay, okay, okay.
Exactly, right? So that is how that is just to generally see. Creep test is what you apply the load, you keep it from a fixed load you apply on the reinforcement, you keep that load fixed for many months. You see what is the change, I mean, what is the elongation of the reinforcement or all those things you note down, right? So now just to accelerate the process, what we do, we keep on increasing the temperature at regular intervals. Okay, and then that result is actually related, some relation is found out, and that is calibrated with the result, and that's all.
ซึ่งในการทดสอบเนี่ยเราก็จะมี initial gauge นะครับอยู่ระยะดึงเนี่ยประมาณ20เซนติเมตรนะครับแต่ว่าเราก็จะใช้การวัดเทรนหรือความเครียดดึงของตัวอย่างเนี่ยครับวัตถุนะครับคือวัตถุนั้นนะครับซึ่งเกจ
So this is the load cell at the top. Inside we have the sample. Okay, so like this here the temperature is maintained. Okay, so slowly they increase the temperature. So inside vacuum is also there, and they increase the temperature step by step at 15 degrees, I think 15 to 20 degrees interval, and we note down the results. Okay, so this is the sample. See, this is the sample. You can see this black color thing is the sample. Okay, this is the heat generator. Okay, that's all. That's the simple, just for knowledge how the thing looks. I decided to show that nothing else. Okay. Now next we have the installation damage image. So what is installation damage? So as I said, while installing, there will be uh, installation of the reinforcement. There will be some damages, obviously, right? So the lab quality reinforcement, the quality of the reinforcement won't be the same. It will get distorted to some extent because of the interaction with the reinforcement, placing, will be pulling it, right? All this carrying from one place to another, all those things. So for that also to calculate these factors actually, so calculate all these factors, various tests are actually done. Okay, so to calculate all these factors, various tests are done. So that's this. So first we saw the creep test. Similarly, one more test, this installation damage test is done. So use the aggregates that is used it is going to be used in the field. We place the reinforcement with those aggregate. We do the test. Then we see how much. We exhume the sample. Then we see how much strength it is coming. We keep on testing. Like this, we need to do the test. Okay. Okay, then this is the connection test that we will. So this is the, see, this is the upper block, lower block, soil block. We have the reinforcement is beneath. This is the geogrid. This is fixed here. Okay, and then you just pull the geogrid. Okay, and check how much till how much strength the joint is actually is stable. All right, that is the connection test, nothing else. Now next we have the pull out test. So pull out test is what? Why is pull out test used? Pull out test is used to determine this interface friction angle. So what we do, we have very similar. So we have the box here, right? We have the box, we have the reinforcement inside, and then we keep on pulling it. So we have some load that is applied here. Okay, load, and we pull it, and this is the what? This is the length LE. Okay, so at various vertical loads, at various vertical pressures we do. So obviously if the vertical pressures increases, the peak pull out load will also increase, and then we can put that in this relation and find out our tan delta, and then from here we can find out the alpha, that is nothing but the interaction coefficient. Okay, interaction coefficient. So generally the interaction coefficient is less than 1, but we can have interaction coefficient of 1 also if we use say geogrids, geogrids with very large aperture size, we are using. At that time, what will happen? At that time, the soil to cell contact is only there, right? The contact is there, soil to cell. So directly soil friction, tan of the soil friction angle we can use at that time. So that time we will have alpha as 1. There are various cases that we will have. So you understood, right? In geogrid, what will happen? Geogrid, if the geogrid is very high aperture, at that time, see, it is just upper soil and lower soil, those will be contact. There will be contact, right? Also there will be some interlocking. There will be some interlocking. So at that time, due to interlocking, this alpha might come more than 1 also sometimes due to dilation. Okay, dilation. Okay, now let us see this pull out test. What? Geomembranes are generally very smooth, right? Smooth sheet kind of thing. No interlocking with the soil particles. But in geogrid, there is interlocking. Okay? No interaction, flexibility is provided by flexible geogrid. Okay? And so here you can see the peak is around at what? Around here, right? 250. newtons. All right. Now we will saw right that for geogrid, due to the interlocking, the pull-out resistance was very high. Okay. Now say we have a anchored reinforcement. So in anchored reinforcement, what the anchored reinforcement, apart from the frictional, this frictional resistance, we have a component from the passive resistance. Okay, so we have a reinforcement like this, which is anchored. So when you pull this side, pull it this side, you will have some passive resistance that develops here. That passive resistance is really given by this expression. The sum of the frictional resistance, the frictional resistance plus the passive resistance will give you the ultimate pull out capacity for an anchored reinforcement. Okay, that reinforcement is anchored. Okay. Okay, we'll solve the problems next. Just before that, I wanted to show you something. Can you tell me where is the world's largest reinforced art structure? World's tallest reinforced art structure. Where
In
is that?
Sikkim. In Sikkim.
Yeah, Sikkim where?
I don't know the exact place, but it is in Sikkim, 100-meter long, 100-meter high, more than 100 meters.
What is the height of the reinforced earth wall in Pakyong Airport? Do you have any idea?
No, but it is 110.
Let me check.
80 meter, Pakyang Airport.
Pakyong is 80. 80?
Maybe. Maybe, I'm
Yeah.
not sure.
80. 80. Yeah, 80. But one more higher than that is there.
Yeah, that is 100, more than 100-meter high.
100 meters. That is where
That I don't know exact location.
that is there in West Bengal only.
Oh,
That is there your this highway near Darjeeling highway, Tindhara. Okay, Tindharia.
Indhara.
Tindharia.
Okay, okay, okay.
Tindharia in West Bengal, in North Bengal, in the this your highway, Darjeeling, the highway that connects the this
Hmm.
Darjeeling with Siliguri and all, Siliguri, Darjeeling district. So that is that. There, one reinforced earth structure is there, the highest, tallest reinforced earth structure, 102.8 meters. That is the
Okay.
world's tallest reinforced earth structure. That is constructed by Terre Army. You might have heard
Yeah,
about the
yeah,
company Terre Army.
yeah.
So Terre Army, actually, I will show you the file. Just a second. It's very interesting for that type of. Okay, this is the world's tallest reinforced structure. Let me just share the screen from my laptop. Can you see? Is it coming?
No, it's not visible.
Not visible. Just a second. Just a second. Okay. Just a second. Huh? I will reshare it. Yeah. Now you can see, right? So Terre Arme constructed. This is the world's tallest reinforced. So you can see this is the highway, and this highway actually failed due to landslide, and there was due to the landslide. So here along the highway you also have our Darjeeling Himalayan Railway, which is the UNESCO World Heritage Railway that is there. Darjeeling Himalayan Railway, the toy train that runs from Jalpaiguri to your Darjeeling. So that railway is also a railway line is also goes here. Toy train railway line also passes, and this is the one of the most important highway that connects the entire Darjeeling and all those regions to West Bengal. So what happens? You can see here. You can see in September 2011 there was a huge landslide. Okay, due to the earthquake, there was a huge landslide that damaged the total road and everything it damaged. Okay, there was a very huge landslide. So they decided that initially it was decided. So here it is written. I will show you. Mm, see, initially the project was tendered and awarded in 2000 using conventional reinforced soil structure with Gavian basis. So conventional reinforced earth structure, the normal reinforced like reinforcement, they will normal reinforced earth structure. They thought that they will use that to construct them. But the main challenge was that the amount of backfill, okay, the amount of backfill that was needed, that would be needed to fill that earth structure was actually huge. Okay, and that's why you can see here. Initially, the project was tendered and awarded to the 13 using conventional reinforced soil structure with Gavian facing. After commencing the construction, the contractor could realize that the requirement of backfill in boulder for such structure was very high, and eventually the project had to be cancelled due to cost overrun. Okay, so eventually they had to cancel the this one due to high cost involved. Then later it was awarded this was awarded to Terry Arme. So see, the owner of the project was Ministry of Road Transport and your PWD roads in roads of West Bengal government, and they actually contacted Terry Arme as a design partner for this project, and the main contractor was SRPL Pioneer, and they were the engineers, but the design for this was given by Terry Army. Okay, Terry Army India. And the Terry Army India, they have a technology called this TerraLink. Okay, they have this technology TerraLink. So using that, they actually suggested the design of this reinforcement. So this TerraLink, what I could understand by reading this is that, so these facings you can see, these are steel mesh facings that they use. Okay, and apart from that, they are using some nailings also and anchors also. Okay, anchors on the reinforcement they are using. And one more thing, these are linked reinforcement. That means generally what do we have? So the reinforcement of this layer, so this layer is linked to the reinforcement, it is tied to the reinforcement at the back of the back layer. Okay, so this layer by layer, these reinforcements are, so generally what happens, we provide reinforcement like this, like this, like this. Okay, that's all. But here what they did, they connected the reinforcement from here to here to the back. So for this layer also, the reinforcement for this wall will be connected to the back wall. Okay, so they use this their proprietary technology, this TerraLink they used to design this wall, and this was actually very successful. The project was sanctioned in 2017, and in 2000 it took around 4 years, and in 2021 it got operational. Okay, so you can see here they are doing this nailing kind of thing they are doing. Okay, so you can see, you will get this file over the internet, you can see this and read this, it's quite interesting. And due to this technology they could reduce the backfill quantity also by large amount. Okay, so the backfill quantity, amount of fill that you have to use, that they reduced. And the innovative TerraLink, as I said, they use this, that could be used in a limited space. Okay, the slope stability, obviously they considered all these things. And so you can see this is the picture during the construction phase. Okay, all these things, all the details are given, you can see this. Okay, this is during the construction, you can see this is the wall and this is the highway it is going, and here you have the railway line. Okay, this is the Darjeeling Himalayan THR, Darjeeling Himalayan Railway. It is going, this is passing like this. Okay, and here we have the highway Tindharia. Okay, and then this is all, these are more pictures, and now you can see, so this is the highway. Now it looks something like this. This is the highway, this is the wall. So you can see this wall is like constructed in layers. Okay, stepwise, stepped wall. Okay, stepped wall they have constructed, and here you can see the other details of the this. Okay, now this is the final picture, you can see final wall and your road. Okay, so this PDF will get over the internet, you can see this, it's interesting, you will get some knowledge. Okay, what type of structure, see nails were also with anchor system, nails, as I said, soil nails you saw, so those were also used. All the properties are given, soil reinforcement, what reinforcement were used, that was given, LDP reinforcement, these were used, what type of fascia they used, welded steel grip, as I said, welded stay use welded steel grip as the fascia, all those things, connection system, what connection system was used, all those things you can see. Okay, and zone 4 seismic coefficient, they used seismic design, they obviously implemented the seismic forces, so 0.24 they used as the seismic design coefficient. Design life was 100 years. Live load, due to the car load, highway load, live load 24 kPa they considered. All those things you can see this file. Okay, this is there in Terrearmes website, so you can refer their website, you will get all these details. Along with that, various other projects, all the details of other projects are also there. Okay, slope protection and drainage improvement at Tindharia, Arunachal Highway 110, previously in Darjeeling district of West Bengal. Okay. World's tallest reinforced earth structure, 102.8 meters. Okay. Now we have some basics, 4 or 5 problems. Those easy problems we will solve. I will solve. Then with that we will end today's session. Okay, so the question is calculate the factor of safety in sliding using the FHWA method for a 10-meter high reinforced soil wall. The friction angle of the soil is 35 degrees and the unit weight is 18 kilonewton per meter cube. Friction angle of foundation soil is 30 degrees. The width of reinforced block is 7 meter. Permanent surcharge is 10 kilonewton per meter square. Live load surcharge is 5 kilonewton per meter square. The maximum possible load in crash barrier is 25 kilonewton. So all loads are given. Just you need to calculate. So tell me what is P? What was P? Neglect. So we'll be neglecting seismic load for now, just for simplicity. But when you solve the problems, you can consider seismic loads and also you can do. Okay. We have to consider generally, but now for just our purpose, we will neglect seismic load. So for P, what was the expression for P? So what are the checks? Sliding, overturning, right? These are the main two checks that you have to do. So it is asked factor of safety in sliding. Okay. First, let us calculate factor of safety in sliding. So what is the horizontal force that is load that is acting? Half KAB right? You saw that already. Now what is KAB? What is KAB? What do you mean by KAB? What do you mean by KAB? KB is the active earth pressure coefficient of what? Which one? Active earth pressure coefficient of
Backfill soil.
backfill soil. So 1 minus how much?
Sine 30, 35. Sine 35.
1 plus.
Sine 35.
So how much it is? 0.271. Now we can calculate P. Half 0.271. What is gamma? 18 times 10 square plus. What is QD?
10 plus 5.
5. Height
Into 10.
pH 95.
25.
So we will get what is the shear resistance? What was the formula relation for shear resistance? Mu friction coefficient times what? How much? Well, the total vertical load that is coming. Right. So what is that?
Yeah, B into L into gamma.
What? What?
B into L into gamma.
Should be gamma into H into L, right?
Sorry, gamma into H.
Plus
Plus dead load.
QD into L.
8 L.
Okay, QD into L. So we will get this as 0. What is the friction angle? How to calculate the friction angle?
10
You can
30.
take 10 2/3 of 5 can take.
2/3 of it. Sorry. 10 20.
Now, therefore, factor of safety in sliding, how much? Safe, right? Safe in sliding. Now, next is for the same previous case, calculate the factor of safety against overturning. Okay, so what was the overturning moment? Please tell. 1/6. Okay. Now next you have to calculate the resisting moment. The resisting moment is coming from the weight L times L by 2 plus QDL times L by 2. So therefore, factor of safety overturning is it safe? Is it safe?
Is greater than 2, so it's safe.
Now see, try to calculate this. Calculate the net ultimate bearing capacity of a strip footing of width 5 meter situated 1 meter below ground level. Soil is dry, having unit weight 18 kN per meter cube. Friction angle is 30 degree. Cohesion is 5 kPa. Water table is situated at grade 10. Consider general shear failure. Now for phi equal to 36 degree, you can calculate NC. You can know NQ. You can know N gamma. From where will you get these values? From where will you get?
IS 6403.
Yes, from IS 6403 you can get NQ and gamma. So if you look at the table, you will get okay. Done. Now see what is the net ultimate bearing capacity given by IS code. Can you tell me the expression of net ultimate bearing capacity given by IS code? IS 6403 CNC
CNC
then
SC SC
DC
DC
IC plus Q.
plus QNQ NQ minus 1 SQ DQ IQ
Then
plus 0.5 B gamma N gamma
S gamma D gamma,
I gamma.
right? Then W dash for water. Now NC, NQ and gamma we got. Now load is vertical, so IC, IQ, I gamma will be 1. Now what about DC, DQ and D gamma? What will be SC, SQ and S gamma?
For strip footing it is 1.
1. So let us calculate, it will be 1. So S's are 1, I's are 1. Now what about DC? Now what is DC? What is DC? 1 plus 0.2 by B. So if we do 1 plus 0.5 root over n pi is nothing but 10 45 plus 5 by 2. So we'll get this is 1.08. Okay. So nq is nothing but nothing but kp. Now what is dq and d gamma? 1 plus 0.1 d by p root over I. So this one will come as 1.04. So now we can put all the values. C, NC, DC, others are 1, Q, Q. Why Q I have taken 18? Why Q is 18? Why Q is 18?
The depth is 1 meter, density is 18.
Right. Gamma times T. And what will be this W dash?
1.
Why?
It is at great depth. Water table is at great depth. Beyond depth of
DF,
greater
DF
than
plus.
B.
Yeah, correct. So we got Q anyways this. So if this is the footing, say this is the ground level, the DF, the B, this is. So if water is below this, then we have W dash equal to 1. If water is here or above, it is 0.5, and between anything in between we need to interpolate. Okay. Now try to do this problem. Calculate the bearing pressure on foundation soil for the scenario as given in problem 1. Calculate the factor of safety in bearing if the foundation soil friction angle 30 degree and cohesion 20. You have to find out. You have to find first. You have to find out the bearing pressure that is coming into the foundation. This you have to find out. So try to find out this. Today first slide of today's class we discussed this, right? Sigma VB. What is sigma VB? RB by B minus 2IC. So do that and find this one. Calculate the bearing pressure on foundation soil for the scenario given in problem 1. So what is R? Gamma HB plus QL plus QD times B, isn't it? Right. So what is gamma? What was gamma? Go to first problem. Gamma was 18. Okay. See all the friction angle of soil is 35. Friction angle of foundation soil is 30 degrees. Other loads you know. Okay. One more thing. Yeah, width of reinforced block is also given 7 meter. B also you know. All these things are given. So directly you can find out 18 into height of the wall was 10. width of the reinforced soil block was 7. 10 plus 5 times 7. This one will come as 1365 kilonewton per meter. Okay. Now what is E? Resisting moment by RV. So resisting moment you already calculated in problem 2. All these are extensions of that only, right? Problem 1 it has been asked. So here this one you calculated 1266.25. So 1266.25 divided by 1365. How much is it? 0.93. So does this satisfy the criteria? Is it less than B by 6? How much is B by 6? It's less than B by 6, right? What is B? 7. 7 by 6 is 1.167. It is less than B by 6, so it's fine. So E is 0.93. Now sigma VB you can find out. 1365 divided by 7 minus 2 into 0.93. So you get sigma VB as 265.56 kilonewton per meter square. Okay. Okay, so this much load is coming on the foundation soil. This much pressure is acting on the foundation soil. Okay, now what you need to do? Calculate the factor of safety in bearing if the foundation soil friction angle is 30 degree and cohesion is 20 kPa. These are the properties of the foundation soil that is given to you. So what you need to do? You need to calculate the bearing capacity of the foundation soil. So our phi of the foundation soil is 30 degrees, less than 36 degrees. So we will consider local shear failure. So we find out phi dash. Phi dash is nothing but tan inverse 0.6. All these are given in IS 6403. Okay. How do you need to do? 1030. So this will come out as 21.15 degree. Now from your table in IS 6403, you interpolate the values and find out for 21.15 degree the value of NC, that will use this much, NQ and N gamma. Okay, then you calculate again DC, you calculate similarly. So it is, I think, coming as 1, and also DQ and D gamma is also coming 1. Okay, then then you calculate similarly again, you calculate the net ultimate bearing capacity. So everything is 1, so directly C and C, right? So C and C plus, now tell me Q and Q. Now what is Q? Now what will be Q? Now what will be Q? Now what will be Q? This is something like
It
this,
will be
right?
RV. It will be RV.
Q and Q minus 1, then other factors, right? N plus half gamma B N gamma other factors. So how much, what will be Q?
RV.
No. What is Q? Q is the, in terms of foundation you think, now what is Q? So this is the soil level. This is the soil, right? This is DF. So what is Q? Q is gamma into DF,
Surcharge.
right? Isn't it? Gamma into DF.
Yeah.
Now, this is your reinforced soil. This is the foundation soil. Now, in that case, you can consider that this block is directly at the surface of the foundation soil.
Okay.
Right, this block is directly at the foundation of the
DF is 0.
is 0. Right, so it will be what? 20 into 16.18 plus 0 plus half gamma b and gamma. Other factors are 0, 1, 1, 1, 1. Here also others are 1, 1, 1, 1. I am not writing it again and again. So this one you will get as parameter. So this is net ultimate. From here you have to find allowable. Allowable is net ultimate. You can take factor of safety as 3. Now what is the factor of safety then? What is the factor of safety? Calculate the factor of safety. 247.52 divided by how much? How much pressure is it coming? 265.56. So it is less than 1.5, right? Less than 1. So it is unsafe. It is unsafe. So maybe you have to increase the length of the reinforced soil block, right? Something you have to do. Because in this case it is unsafe. Okay, or maybe you cannot construct or maybe you have to strengthen the foundation soil to increase its file. Something you have to do. Okay. Now do this last problem. Calculate the allowable tensile strength for a geotextile with ultimate tensile strength is 200 kilonewton per meter. Okay, this is from corner to be used for slope stabilization. So just look at this graph and then find out the values and take T allowable is equal to T ultimate. This is by corner, okay, corner. So I am writing his expression, corner's expression. So 200 divided by what is installation damage for slope stabilization? 1.1 to 1.5. So let us take 1.5 for creep. Creep is 2 to 3. So let us take 3. Chemical biological damage CBD. On to 1.5. So let us take 1.5. Nothing but 29.63. Now see, the main point of doing this problem is that in lab you tested that your ultimate tensile strength is 200 kilonewton per meter. But you can see by using the factors it almost reduced by 10 times. Almost 10 times, not 10 times, lesser than 10 times, but almost 10 times it got reduced. So that much factor of safety we are actually taking when we are designing everything. Okay, because whatever values we get in lab conditions are very like controlled conditions, right? So that we cannot trust. So we reduce the ultimate tensile strength by large amount. From 200 we reduce this to 29.63 kilonewton per meter. Okay, on that we do all calculations. Okay, so in the next class we will solve all these easy design problems. But I know we won't get some time. So if you
You are not audible.
yeah. Yeah, so I was saying that solving some problems from our design of reinforcer. So please check whether if week 5 lectures are released or not yet. Is it released? Week 5 lectures?
Yes, it is released.
Okay, then good. Then you can go through, please go through the week 5 lectures before Tuesday so that we can solve some basic problems. Okay, so please see those lectures in the next class. We will solve some problems. So next class will be, next lecture will be on Tuesday 20th of August to 8 p.m. Okay, Tuesday 20th of August, that is day after tomorrow, from 20th from 6 to 8 p.m. So on 25th, next Sunday, we won't be having any discussion session. That session we have preponed to Tuesday. Okay, as I have to travel somewhere, so so we made these changes. So Tuesday we'll be having the 5th week discussion session from 6 p.m. to 8 a.m. 20th of August on Tuesday. Okay, so with this we will end today's session, and I hope everything was clear, and if you have any doubt you can always let me know. And so thank you for attending, and see you on Tuesday. So before that, please go through the week 5 lectures before the discussion session on Tuesday. Just see the lectures once. Okay, so okay, thank you so much for attending, and have a very good evening. Thank you. See you on Tuesday, day after tomorrow.